We continue now in Chapter 28 on the sources of magnetic field with Section 28.3, this module. Module 28.3 concerns the force between two infinitely long parallel conductors. And you can see how this arises because we have already taken 28.3. We want to look at two infinitely long wires, and the reason that this is very important is it's used to define the ampere itself. And if we have a current I which flows here and another current I which flows here, and let's call these I1 and I2, this current I1 gives rise to a magnetic field here on I2. And of course that magnetic field causes a force on this wire here to either push them apart or pull them together. Let's see if we can figure out what the directions are here. Well, as this wire I1 creates a magnetic field, that magnetic field goes around here and goes in there, and it would come back around on the back side of that wire, assuming the current's going up. This is exactly like the right-hand rule, with the fingers going into the paper and coming back out on the other side. So the magnetic field is going, B is going into the paper here, because these are parallel and lying along the paper. So this goes into the paper. Now we have a B going into the paper and an I going upward. And you recall what our force was. Our force before said we had an infinitesimal force that came from a current. That would be a force on a current that would have a length dl cross a magnetic field B. Well, we know from an infinitely long wire what our current is, what our magnetic field is. So this magnetic field that goes into the paper is going to be equal to mu naught I over 2 pi A. And we just had that in the last section. Well, now we're looking at another piece here that says, another section that says, if we have that magnetic field at this point, this wire here is going to experience a force, an infinitesimal force due to that magnetic field. What we're going to do is divide by dl, because obviously the length is going to feel an infinite force due to an infinitely long current. So we can actually say the infinitesimal force per unit length is going to be equal to I times that magnetic field. But this is I2, because it's I2 that finds itself in the magnetic field. So this is going to be equal to, substituting the B into here, mu naught I1 I2 divided by 2 pi A. And that is precisely what we find as the force per unit distance is mu naught I1 I2 over 2 pi A. This is the infinitesimal force per unit length. I can just write the force per unit length for two infinitely parallel wires. And that means that we can actually take a current of 1 amp here and 1 amp here and put them apart by 1 meter. And this is saying when we do that, then if we have 1 amp here and 1 amp here, put them 1 meter apart, our force per unit length will be exactly mu naught over 2 pi. You remember mu naught over 4 pi is equal to what? Mu naught over 4 pi is equal to 1 e to the minus 7th. So this would be twice that much if it's over 2 pi. So 2e to the minus 7th is the force per unit length between two 1 amp currents a distance of 1 meter apart. And that's used to actually define the ampere. Once we define the ampere, then of course we can define the coulomb. Now, what force is that going to be? I often ask that question also, not just the magnitude of the force per unit length, but what direction will it be? Well, if both currents go in the same direction, what will that give us? Well, if this current goes this way, the magnetic field comes around here, so it's going into the paper. And you remember the force is dl cross B. So the magnetic field is going into the paper here. dl is going up. So dl cross B, dl, let's see, I've got into the paper, dl cross B, dl is that way, B is into the paper, so dl cross B is attractive. So this is attractive. If I1 and I2 in the same direction.